Good afternoon, everyone. I'm Yan Taoli from Chongqing University, China. Due to the visa issue, the others cannot attend this conference in person, so I will present this work as a proxy presenter. So the title of this work is Improving the Accuracy of Locally Differential Private Community Detection by Order Consistent Data Perturbation. The authors are from Chongqing University, Chongqing Normal University, China, CSIRO, Australia, NTU, Singapore. So I will introduce this work in the following sections: background, existing method, key findings, solution, experiments, and conclusion. So let's see the background of this work. Community detection is a fundamental task of network science. It aims to partition network nodes into a set of subgroups, such that nodes in the same group link to each other more densely than other groups. It has two types of participants, users and the server. Users publish their social links with friends to the server. The server gathers users' links, builds social graph, and performs the community detection from the social graph. In this paper, we assume that the server is not under the control of users, and hence it is untrusted. This is because the server faces various security threats, such as intrusion attacks and inference attacks. It collects and stores a large number of users' social links, which pose a serious risk of privacy leakage for users. Therefore, protecting social links in community detection has attracted increasing attention from researchers. Local differential privacy is a privacy data collection framework. As illustrated in the figure, each user's raw data is locally perturbed by an LDP randomizer to generate noisy data, which is then published to the untrusted server. The untrusted server carries out data analysis task based on the perturbed data from users. A randomized algorithm M is epsilon LDP if and only if this equation holds. Our work is partially based on the existing method called LF-GDPR. It is a generalized framework for estimating graph metrics with LDP protection, which can be used for detecting communities based on perturbed user links. For any given user U, LF-GDPR encodes his social links into a 0-1 sequence. 1 or 0 indicates the non-existence or existence of a link between users U and V. Then for each social link X, U, V, LF-GDPR maintains it unchanged with a probability and changed with another probability. Finally, LF-GDPR aggregates the perturbed links of all users and detects communities using the Louvre algorithm. LF-GDPR faces the challenge of generating lots of fake edges, leading to a poor detection accuracy. We take the Facebook Ego Network dataset as an example. The dataset includes more than 4,000 nodes and 88,000 social links. When perturbing user links with LF-GDPR at a privacy budget of 1, it is expected to return more than 64,000 true edges and generate more than 4 million false edges, resulting in 98.5% false edges. We find that the utility requirements and the privacy protection goals are inconsistent. Reasons for the poor accuracy of existing methods are that data perturbation disrupts the fitness ordering between users and groups, causing community detection algorithms to fail in placing users to more suitable groups. The motivation behind this paper is that if we can place users in the fittest community groups from the perturbed data, then we can guarantee community detection accuracy. In this work, we propose a locally differentially private community detection method, namely LDP-CD. It consists of two phases, user grouping and grouping optimization. The user grouping phase microscopically groups all users initially through LF-GDPR. The grouping optimization phase microscopically analyzes the fitness of each user to community groups and places them in the fittest group. Because of the two phases, we divided the privacy budget epsilon into two parts, epsilon 1 and epsilon 2. So epsilon equals epsilon 1 plus epsilon 2, which are used in the two phases to preserve the privacy of users' social links. Next, I will detail these two phases. For the first phase, LDP-CD follows the user coding method and data perturbation method of LF-GDPR, but we use the privacy budget of epsilon 1. Based on this, we estimate each user's degree, the number of links in the social graph, and the number of links in each community from the perturbed social links. These estimates are then used in the Leuven algorithm to obtain the initial community grouping. For the second phase, we perturb social links of the users, as shown in the figure right. First, for any given user U, we count use degrees within the community groups identified in the first phase. Then we sort the degrees of U in an ascending order. Next, we add a Laplace noise to the use degree vector using the privacy budget of epsilon 2. After that, we sort the perturbed degree vectors with the optimization objective of minimizing the two norms between the sorted and perturbed degree vectors. Finally, we recover the ordering of the perturbation results based on the true order of the users and the community groupings. We optimize the user grouping results obtained in the first stage from the ordering consistency perturbed degree vector of users with community groups. First, we compute the fitness of users with the community groups from the perturbed degree vectors. Then we calculate the modularity gain of moving users from their community to other communities, migrate users with low fitness to the community with the highest one, and update the fitness between users and their communities. On this base, we iterate the above process until user migration no longer increases users' fitness with their communities. For experiments, we select two publicly available data sets, Facebook Ego network dataset and a government network dataset. For comparison, we choose two state-of-the-art methods, LDP-Gene and LF-GDPR. Our metrics include majority, fitness, ARI, and AMI. These two figures illustrate the community detection accuracy of LDP-CD and the comparison methods on the various privacy budgets in Ego network and government datasets. We have two conclusions from the experimental results. The first is that our method provides more accurate detection results than comparison methods. For example, on the Facebook Ego network dataset, with the privacy budget epsilon equals 5, the four metrics of our method are higher than LF-GDPR and LDP gene. The same results go to the government network dataset. Therefore, we can conclude that LDP-CD has better community detection accuracy than the other two methods. The second conclusion is that our method provides a good trade-off between user privacy and community detection accuracy. A good trade-off means a significant increase in accuracy as the privacy budget increases. For example, on the Facebook Ego network dataset, as the privacy budget increases from 1 to 5, the fitness of LDP-CD rises from 0.2242 to 0.7646. The fitness of the other two methods also shows increase. Thus, both of our method and LF-GDPR can trade off user privacy against the detection accuracy, but our accuracy is consistently better than that of LF-GDPR. So let's conclude this work with our contributions. We propose LDP-CD, a novel framework for community detection under LDP. We find that community detection relies on the order of users' fitness with community groups rather than their social links or degree vector. We experimentally compare LDP-CD with two state-of-the-art methods on two real datasets. Thank you for your attention.